Hello everyone, it's 1 p.m. Eastern and that means it's time to begin our first CoCoRaHS Weather Talk webinar here in 2017. Thanks for joining us today. I'm your host Henry Regis. Running the technical side of our program is our very own Noah Newman, and we're coming to you live from Colorado State University, the Colorado Climate Center here in fairly mild and it looks like mostly sunny Fort Collins, Colorado. For those of you who are unable to join us for our live broadcast, we'll be recording this one for future viewing on our website. All of our Weather Talk webinars are sponsored by generous donations from listeners just like you. Well, if you're interested in satellite images and satellites in general, this webinar is for you. As we take a comprehensive look at the GOES-R satellite, well, now it's orbiting the Earth as GOES-16, and it will definitely be another one of our I need to throw this pun in there. Out of this world webinars. There we go. With us today is Matt Rogers. He's a longtime friend of CoCoRaHS and actually our next door neighbor here at Colorado State University. He's a researcher for CIRA. That CIRA stands for the Cooperative Institute for Research in the Atmosphere. Well, Matt splits his time between research using observations of cloud and other atmospheric properties from satellites and performing public relations, education, and outreach duties for CIRA. Perhaps you've seen him do one of these locally or somewhere across the country. He has worked on the NASA CloudSat, let's try it again, CloudSat and orbiting carbon observation missions, and now works in the Meteorology and Satellite Applications Group at CIRA. Also of note, Matt grew up in Colorado, right here, not too far away, and is a longtime Denver Broncos fan. At age 16, he watched an IMAX film on storm chasing at the Denver Museum of Science, and right then and there, he knew what kind of career he wanted to pursue. Well, welcome, Matt. It's great to have you on our broadcast today. Tell us, you were bit by the weather bug at 16. When did you become interested in satellites?
Well, hi, Henry, and hi, everyone. So I'll tell you, satellites was actually something that came along as I was in college. I went to the University of Colorado at Boulder and majored in physics and minored in atmospheric science. And my minor advisor there was a guy named Dr. Frank Evans, who did a lot of work with satellite remote sensing. And that kind of got the bug going for me there at CU.
Well, great. Hey, thanks for being with us today, and I'm going to pass the controls over to you, and we'll take questions after Matt's presentation.
Okay, can everyone see the screen? I want to make sure we're set up properly.
We can, yes.
Okay, great, thanks. So again, my name is Matt Rogers, and I am a research scientist at the Cooperative Institute for Research in the Atmosphere here at CSU. There's about 18 of these cooperative institutes that operate between various universities and NOAA, the National Oceanic and Atmospheric Administration. And the idea is a partnership between academia and the federal government to bring the best of research into operations. And so a lot of what we do here is find ways to get next generation research into the products that everyone uses for their weather forecasts. And a lot of what we do here is related to GOES-16, as Henry pointed out. It's when we signed this all up, it was all GOES-R. But now the satellite is actually in a quasi-operational state, and so it's GOES-16. So just to give you an overview of what we're going to talk about today, we'll talk a little bit about the launch, which is always fun. Anytime you're doing satellite work, you have to deal with rockets, and that's always a neat thing to look at. Just to fill in the background, I looked at everyone filled out a survey, and I want to make sure that we have everyone on board with the science behind it. So we'll talk a little bit about basic orbital mechanics, and then some of the basics of electromagnetic radiation, and how we use that for satellite remote sensing. There's probably a couple of experts on the topic on the webinar this time, so that'd be a good time for you guys to go get a cup of coffee if you want, or hang around and see if you learn anything, and then everyone else can get up to speed on what we do. Then we'll look a little bit more at the basics of what GOES-16 has to offer. The instruments on board, what we can do with those, and then some of the applications for how those observations are really going to be useful going forward in the future. So looking at the launch of GOES-16, we had a very successful launch November 19th, 2016 in the evening. I did not get to go to the launch. It was right in the middle of my daughter's piano recital, but we did get to see it recorded. We launched from Cape Canaveral Air Force Station in Florida at the SLC 41 Space Launch Complex 41. The launch vehicle was an Atlas, a United Launch Alliance Atlas 5. It's the 541 model in case any of you are looking to get your own. That comes with the standard 5-meter fairing, 4 booster rockets, and then 1 Centaur upper stage to get to geostationary transfer orbit. And we'll talk about what all those things mean. If you are looking to pick up your own, it's about $104 million. So, you know, save your pennies. We did launch about 15 days late from the ideal launch window, and that was ironically due to Hurricane Matthew, which, as you remember, was just working its way up the Florida coastline. We had just landed the GoSAR spacecraft, and it was in a holding facility just west of the launch site as the hurricane went past. Fortunately, there was no major damage to the rocket or the spacecraft, minor damage only to the launch facility. And when they got everything checked out, we launched about 15 days late. The total cost of the mission, you always get asked this. The entire program for GoSAR is $10.83 billion. That started back in 2005 with a planning effort to create you know, the mechanisms to develop this next generation instrument. That does include 4 spacecraft, GoSAR, which is now GO-16, GOES-S, which has actually been built mostly, and they're going through some ground tests on that, and then GOES-T and GOES-U will follow up afterwards. And it's about a 30-year program to spread all that money out. I think when you look at the benefits of what these satellites offer, you'll realize that that's quite a good deal. So here's a picture of the rocket. This is your Atlas 5 541, and you can see these 4 booster rockets here. That help you basically get off the pad and get through the thickest part of the Earth's atmosphere. This is the Atlas Common Core booster that gets you out into space, which then separates, leaving you with a Centaur upper stage, and that's the stage that actually gets you mostly to your geosynchronous transfer orbit. And then up at the top of the rocket here is the GoSAR spacecraft itself, GO-16. So it's always fun to show launch videos. This is a pretty neat one that NASA has put out, and we'll watch a part of it. We won't watch the entire thing, but there are links to this online at the end of the webinar. Oops, wait, that didn't work right. Let's try that again. You have to click on the right spot. So again, this is put together by the GoSAR program, and we're going to be zooming in here to Cape Canaveral Air Force Station at 5, 4, 3, 2, 1, and liftoff of the Atlas V rocket. It heads off into the sky and does a roll program to tilt it. About a minute and a half into flight, those solid rocket boosters burn out. Uh-oh, we seem to have paused and separate and fall away. The Common Core booster gets you up into the atmosphere. Once you're out of the atmosphere, you can jettison that fairing. You don't need it anymore, and it's just extra weight. And eventually, you'll have booster engine cutoff here, and then the aircraft separation. So that first stage is gone, and that Centaur stage now lights up to get you to a low Earth orbit, and we'll talk about what that means in just a minute. Here's a kind of trace to see where that happens. You launch, you head out over the Bahamas, you get separation right over the Bahamas, and then a continued flight to the southeast, kind of off the coast of South America. You reach your first coast phase right about there, so you can see heading towards the Amazon Delta. And then there's a second burn that comes up to get it from its low Earth orbit to a much higher orbit. And so this burn happens for quite a long time. And again, we're timing out a little bit. It worked much better yesterday. So it burns for a little bit, and then it coasts for 3 hours. And we're going to skip a good chunk of those 3 hours because we don't have that much time. But as the spacecraft is coasting towards a much higher orbit, it starts off at this kind of higher orbit. And then what's going to happen is the engine on the spacecraft will then burn to help boost you to a higher orbit. And we call that orbit raising to get to the full geosynchronous orbit. So the spacecraft will roll around. It has a small motor that it will fire to angle itself. It's doing all these maneuvers remotely piloted. And then you'll see this orbit animation as it swings around. Here at the bottom, you'll see these notations where it says LAE burn, and that's when it's firing the engine to speed the spacecraft up and get it up to a much higher orbit. This is over the process of several days. You know, the first part takes you 3 or 4 hours to get to this low transfer orbit, and then over the next several days, you're doing these coordinated burns to get to a much, much higher orbit, and that takes you all the way to a geosynchronous orbit at about 22,000 miles. Once you're there, 7 days into the mission, you deploy the full solar panel and set up the solar instruments that look at the sun. And then you basically stash everything away. And that's kind of where we left GOES-R back at the end of November, early December, with various maneuvers and other kind of housekeeping. Where GOES-R is now, once GOES-R made orbit and became operational, they renamed it to GOES-16. That's kind of a fun leftover from some of the earlier satellite agencies. It's much easier to keep all your satellites in order, so you don't have to remember if GOES-15 crashed or if GOES-12 didn't make it for whatever. You give them a letter designation when you launch them, so if there's a launch failure, which does happen, then you can move to the next launch number, and you keep all your numbers in order. So there's always a GOES-12, always a GOES-13, 14, 15, and 16, in case you're curious. Now the orbits themselves, for those of you that aren't familiar with how orbits work, you can go back to a basic science experiment that maybe you learned when you were in high school, where if you drop something off, say, a desk, it falls to the Earth. And if you push something sideways off a desk, as it goes off the edge of the desk, it'll still fall, and it'll take exactly the same time to fall as if you dropped it. It also goes sideways, and that sideways motion doesn't affect the time it takes to fall. So you can imagine going faster and faster and pushing things off of a desk or perhaps firing it out of a cannon, and it goes sideways with a certain velocity, and it falls with a certain velocity, and it always falls with that velocity. The trick is, if you go fast enough, it'll, you know, your object will go sideways, and then it'll fall. But the Earth, at that point, if you're going fast enough, the Earth is kind of curving away from you, as it's a nice spherical Earth. So you fall, but you find that the surface of the Earth is kind of below you, so you continue to fall while you continue to go sideways, momentum being conserved as it always is. And essentially what an orbit is a certain speed that you can go sideways where you will constantly fall, but you'll constantly be missing the Earth because you're going fast enough. Typically you want to do this in outer space. It would technically work in the atmosphere if you could overcome the resistance of the atmosphere and were able to avoid things like mountains and buildings. Much easier to do in space where there's no air resistance because you can maintain that sideways speed without having to have continual thrust from a rocket or something else. So you get into space and most of your rocket energy is spent going sideways so that you're essentially missing the Earth. And the faster you go, the more you miss the Earth by. And that's kind of what we're seeing here. There's different types of orbits. You can orbit over the equator, you can orbit from pole to pole, and this is a fairly handy orbit, or at some inclination. The shape of the orbits, you can either be circular or you can have these elliptical orbits where you miss the Earth by very little at one side of it and then miss the Earth by a lot on the other side of it. And then altitude is kind of relevant to what we're doing here. Low altitude orbits, 60 to 1,200 miles, 100 to 2,000 kilometers in metric units. There's a lot of satellites here. This is where your space shuttle orbits around 300 miles. A lot of research satellites are about 400 miles up. And this is a very handy orbit because you don't need a very big rocket, and you can develop less expensive satellites that can give you really good resolution and quality and test things out relatively inexpensively compared to going to other orbits. The other nice thing about these low orbits is that you can do them from pole to pole. So you're constantly going from the South Pole to the North Pole and back to the South Pole. In the meantime, the Earth is rotating underneath you, so you're using the rotation of the Earth as a way to scan. So if you want a satellite that can see the entire planet, one of these polar orbiting low Earth satellites is the way to go. If you want something, on the other hand, that's looking at one part of the Earth all the time, say you want to see where the clouds are moving over your country, then what you want is you want to miss the Earth by more and more, and you want to go over the equator until you're going around the planet, the Earth is rotating underneath you, so there's some rotation of the Earth, and there's a certain speed or a certain distance you can go out to that will give you that speed, or that speed that gives you the distance, where you're going around the Earth, missing it, at the same speed that the Earth itself is rotating. So really you're kind of frozen in one spot over the Earth. And that's what we call a geostationary orbit. You're stationary over the Earth, hence geostationary. And And that turns out to be about 22,300 miles away. So remember, astronauts are about 300 miles away. GOES-R, GOES-16, has gone out to 22,300 miles. So that's a fair ways out there. And it requires a fairly big rocket like the Atlas V to get you there. So that's the basics of orbit. What we have here is a satellite that's designed to look at our side of the Earth pretty much constantly, day or night, and that's a geostationary orbit, and that's useful. So shifting gears a little bit, for those of you who are not familiar with electromagnetic radiation, this is a quick primer. It's basically from your physics class, if you ever took one, your oscillating electric and magnetic fields make these waves, which we call electromagnetic radiation. And everything in the universe, as it turns out, creates an electromagnetic field, and it depends on the temperature of the object. So you sitting at home, right in front of your computers, are emitting electromagnetic radiation. And you may hear me call it just radiation. Electromagnetic radiation is 9 syllables. Radiation is 3 syllables. But when I talk about radiation, I'm talking about electromagnetic radiation, not something that's going to make you grow a second head. So just keep that in mind. So another way to think of it is different colors of light, and I think that's what we put in the questions that we sent out. Electromagnetic radiation is light, and there's just different kinds of light. There's 3 things you can do with it. Light can be scattered or reflected, light can be absorbed, and light can be emitted. And anything that's absorbed can then be re-radiated at a different length. And here's what we mean by that. These are all the different kinds of light there are, basically. We call it the electromagnetic spectrum because we like big words. But essentially what you're doing is you're looking at how big that light ray is. And this is a pretty good chart. You can think of radio waves, which we're all familiar with. Microwaves, those of you who've ever burned a cup of coffee in the microwave know what this is about. Infrared radiation, visible light, ultraviolet light, X-rays, and gamma rays. So these are all things that you may have heard of before. And this is kind of an about the size of chart, which is fairly handy. A lot of times scientists will talk about light mostly in the infrared and visible, which is what we're looking at. We use a lot of microwave as well. And we talk about the size of these beams in terms of millionths of a meter, or microns. And 1 micron is about 1/100th of a sheet of paper. So a sheet of paper, regular copy of paper, is about 100 microns thick. For visible light, you're looking at half of one of those microns, roughly, give or take. And in the infrared, you're looking at 2 microns to 10 to 11 to 12 microns. But to give you a size, pinpoints are about 10 microns or so. Visible light is about the size of a protozoan. Ultraviolet, which you've heard about with the UV layer and the ozone layer, about the size of molecules and then getting smaller. The other thing that's critical is that what creates the light is the temperature of an object. So the temperature of the Earth, the average temperature of the Earth is around 80 Fahrenheit, which scientists like to use in this Kelvin unit, okay? Which that turns out to be about 300 degrees Kelvin. So if you go to 300 degrees Kelvin on this very logarithmic scale, you can see that the Earth would emit primarily infrared light, okay? The Sun, which is, an average temperature of about 9,800 Fahrenheit, or at least the part we can see is, that's about 5,700 Kelvin, which is kind of here-ish. And you can see that that light, the Sun, emits visible light. And you can even see the rainbow, the spectrum of colors of visible light that Sun emits. So a lot of what we're looking at are these different kinds of light and the objects that emit them, which depends on their temperature. And that's the summary here. This upper chart, you can see that the Sun emits most of its light somewhere around half of a micron, with the longer colors, the reds, the orange, and the yellows being on the longer side of that, and the greens, blues, and violets on the shorter side of that. You can see it does emit a little bit of ultraviolet as well, and even shorter wavelengths, and then it emits kind of this long tail into the infrared, okay? The Earth down here at 288 Kelvin, I did a little bit of rounding there, I'm a physicist, that's what we do, is emitting mostly in this kind of 9 to 10 micron band. So there's a little bit of overlap. The Sun emits a little bit of light that the Earth also emits. But if you're building a satellite, you can build an instrument that's designed to look at light emitted by the Sun and light emitted by the Earth. And again, remember, light can be emitted, absorbed, and scattered. And this image of the meerkat, I think, is a fairly handy way that gives us an intuitive understanding of how that works. This light bulb here is emitting a nice infrared lamp, and this meerkat, more specifically the meerkat's tummy, is doing a very good job at absorbing that radiation. So that kind of talks about how light is absorbed and emitted. Also, light can be scattered, and that's what this image is here. Different things in the atmosphere can scatter that light, or light can scatter off the surface of the Earth or scatter off the ocean. And depending on what it's made of, it'll scatter differently. So if it's water versus rock versus a meerkat, these things will all scatter light differently, and scientists can use that to learn more about the properties of the thing doing the scattering. So satellites collect light from many sources. It can be light that's emitted by the sun and then scattered by the Earth, either by the atmosphere or by clouds or by the surface of the Earth. It can be light that's emitted by the Earth or some of the things that are on the Earth, and we'll see some examples of that in just a few slides, or combinations of both. So that's kind of a background of how we look at electromagnetic radiation and orbits. When you're building a satellite, you pick an orbit that puts you where you want to see the things that you want to see, and you build instruments that look at the kind of light that you want to look at based on whether they're emitting, absorbing, or scattering. And with that, you can all apply and have my job. So moving on to our current series of these geostationary operational environmental satellites, which is what GOES stands for. It's a geostationary orbit, so 22,300 miles away, looking at the same part of the Earth all the time. The current series, prior to GOES 16, that is, had one visible channel, so one light looking at, or one channel looking at light from the sun, a near-infrared channel, a water vapor channel, two thermal infrared channels, which are looking at all light emitted from the Earth, and then a sounder instrument that used a bunch of different colors of light to look at the vertical structure of the atmosphere. And we won't talk about that too much. Right now there are two operational satellites, GOES 13 and GOES 15, also known as GOES East and GOES West, which give full coverage of the continental United States. The image you see here is from GOES West, which is above the equator at about 135 degrees west, so off the coast of the Pacific, which gives us a good view of the storms coming in down the Pacific storm track. So here's some of the images from that GOES West, and this is an older image that I like because it kind of demonstrates the different colors of light. So in the upper left, that's a visible image. That's visible light coming from the sun reflecting off the Earth. And you can see where the clouds are. You can see some mountains. You can see some details in California where there was a big drought. And you can see some nice clouds off the coast. The upper right image is an image much more in the near infrared. That's at 3.9 microns. And what you're looking at there is it's a color of light that's really good for nighttime fog, for fire, and then for surface and cloud properties. It's also a good way to find clouds at night when there is no sunlight, because this is light that's kind of emitted by the Earth. Okay? In the bottom left, this is a particularly useful channel at around 6 microns. We call it the water vapor channel, and it's basically a certain kind of light that's emitted by water vapor in the atmosphere. So where there's not very much water vapor, as you can see here moving in over the coast of California, all the way through Nevada and into the northern part of Utah and a little bit further in, you can see where it's very dry, and you can see much more moisture patterns over, say, the Gulf, over the plains. You can see thunderstorms over Colorado, southern Colorado, northwest Colorado, and through Utah. And that tells us where the moisture is, and that's very useful for weather forecasting. And again, this is just a color of light, a kind of infrared light that's emitted by water vapor that we've put on an instrument to measure that. And then the bottom right is actually that thermal infrared. It's looking at the temperature of the Earth. And what you're seeing here is you're seeing these red blobs, and those are the very cold tops of clouds versus the comparatively warm surface of the Earth. And you can tell a big difference between the surface of the ocean, which is much cooler than the warm surface of the Earth, which doesn't compare to the very coldness of the clouds. So scientists are always looking at these different channels of light, these different kinds of light, these colors of light, to tell us interesting things about the Earth. So what does GOES 16 bring over what we currently have? Well, we have a new instrument. It's called the Advanced Baseline Imager, and that's replacing the GOES Imager instrument, which provided the examples you just saw. There's something called the Geostationary Lightning Mapper, which is the first of its kind on, I think, a geostationary platform. Maybe not the first of its kind, but this is certainly a good one. That's going to help us see lightning, and there's lots of things to learn about that. The horizontal resolution, we'll talk a little bit about that, but it's going to be much better. And the time resolution is much, much better as well. We're going to get many more images per hour. And then for the first time, we have this rapid scannability. We can focus in on a 1,000 kilometer by 1,000 kilometer box at 30-second resolution, so we can see incredibly fast detail. So here's the advanced baseline imager. This is the new hotness. This is what's on the satellite that we're all very excited about. The images you saw prior were from the current GOES imager. There's 5 channels on that, and I showed you 4 of those channels. The new Advanced Baseline Imager, or ABI, has 16 of these channels, so there's way more information for scientists to look at and discover things about the planet. When you look at resolution, this is when we talk about going from standard def to high def, or even 4K, I think. Our current GOES is looking at about 1 kilometer, or about 1,000, almost 1,100 yards wide, so that's a pixel, a box on the Earth that's 1,000 yards by 1,000 yards. And our red band on ABI is going to be down to 545 yards, so much smaller. The other visible channels, looking at other colors of visible light, things emitted by the sun, are at 1 kilometer. The infrared channel for the new satellite is at 2 kilometers, or about 1.25 miles, compared to 4 kilometers, or 2.5 miles for the old thing. So we're 4 times better. And in fact, one of the channels, the water vapor channel on the old GOES instrument, is 8 kilometers. So this is a much, much, much higher definition picture that we're getting of the Earth. And that's going to give us a lot more detail and useful things. The coverage is what I'm really excited about. Right now, we're scanning the Earth, the entire planet, everything that the satellite can see, about 3 times per hour. We'll get 4 of those with the new satellite. Looking at just the continental United States, which is what CONUS means, continental United States. Currently, we're getting about 4 per hour. That moves to 12 per hour with the Advanced Baseline Imager. That's 5-minute data versus 15. So we're getting 3 times as much data at higher definition. And then the really exciting thing is this mesoscale, this rapid scan. If there's a tornado outbreak somewhere in the Midwest, or if there's a hurricane coming on shore, we'll be able to zoom in on just that part of the Earth and look at it at every 30 seconds, which is going to give us a ton of detail on the development and the forecast tracks of these storms. And that's a capability that we just don't have right now. The geostationary lightning mapper, and this is a picture of that instrument in its clean room. It's what's called a staring CCD imager, and essentially that's just a camera that looks at a certain color of light that's tuned to what lightning looks like, and that camera refreshes every 2 milliseconds, and it's looking for changes in light intensity. When you get a lightning flash, it'll show up as a brief blip during those 2 millisecond periods, and then you can kind of integrate over all of those images and find where the blips are happening. And that gives us information on the frequency, location, and spatial extent, or where that lightning is happening. There's a lot of applications for how this works. The stronger a storm is, typically the more lightning you get out of it, certainly during the development of that storm, as that storm is kicking up. That's going to help us see where the strongest cores are of supercell thunderstorms. That'll give us improved tornado warnings. And hurricane forecasts, the thunderstorms that make up those individual hurricanes, we'll be able to see where the strongest part of that is. Instead of just looking at a picture from the top, we'll be able to see in it. Obviously, with aircraft routing, you can imagine getting aircraft past dangerous parts where there's lots of lightning. Wildfire forecasting is a big deal. A lot of wildfires are started by lightning. Flooding seems curious, but if you have a really strong thunderstorm, that's going to have a lot of rain as well. So that's one of the signals that you have a really strong developing thunderstorm where you have lots of lightning. And then there's a whole bunch more that we're really looking at, as a research institution to see what we can get out of this instrument. And all of that says we can take the old black and white picture of the Earth and use all those different colors, red, green, blue, infrared, everything we need to come together and give us a full color picture of the Earth. And the imagery you're going to see in the next couple of slides are not from GOES 16. Right now, GOES 16 is kind of in a holding pattern. They're checking out the instruments. They're getting some initial data downloads and checking out to make sure that everything is working properly. I think any time now we're probably going to see some preliminary imagery from GOES 16, and of course that will be looking at the United States. What you're seeing here is an image from a satellite called Himawari 8, launched by the Japanese Meteorological Agency. And that data is coming from an instrument that's almost a direct copy of the Advanced Baseline Imager, called the Advanced Himawari Imager, that has essentially the same channels. And we've been spending the last couple of months using that data from the Japanese satellite to tune our algorithms and our programs to make that data work for the ABI on GOES 16 once we're ready. And here's how that works. You start off with a red channel. So this is a black and white picture of the Earth. This is the color red. We have other channels that are green and blue. We can add those together to make kind of a color picture. And that's nice, but you can kind of see it looks a little hazy, and that's just how the atmosphere works. There's a lot of scattering. Remember, light can be scattered. So if you use your laws of physics cleverly, you can go through and take into account all of the scattering, that Rayleigh scattering of the light on the Earth, and then subtract that out, which gives you a much clearer picture of what's happening at the surface of the Earth. Okay. Once you do that, you can actually then do some color correction and try and get it to see what a human eye would see, which is really useful for forecasters. And that's what this image is, bringing in some more of the green. This image compilation was brought together by one of the senior scientists here at CIRA. His name is Dr. Stephen Miller. And he and his team have been working very hard to put these things together. So I want to make sure to give him credit for this series of images. And you're going to see a lot more of this product once the GOES 16 ABI data becomes available. We'll be able to see the Earth really in beautiful true color, and that helps determining what's going on the Earth. So the next couple images are applications. What can we do when we have these true color images? And these are from another colleague here, Curtis Seaman at CIRA, who gave us these images. And these are actually from one of these low altitude satellites that are flying over the Earth. We can kind of test things out. And we developed different products called natural color or true color. Natural color helps us learn things about clouds. True color is kind of what our eyes would see. And one of the applications that are really useful are flash floods. Okay, looking at the Earth, it's difficult to kind of tell water from dark backgrounds, but if you can put it in color, water, of course, looks blue. So this is from the 2nd of June 2014 to the 30th of June 2014 in Argentina and Paraguay. You can see a river here in the upper left that is at its normal stage. They had a series of heavy thunderstorms that then brought in a bunch of rainfall that then all worked its way in this river, and you can see this much wider area in the upper right that showed the extent of the flooding. And that's something you're going to be able to see in remote areas where you don't have, flood gauges or other ways to monitor the stages of flooding rivers. This will give us advanced warning of these flash floods and help us study floodplains and find better ways to deal with these potential natural disasters. Another application, vegetation and leaf biology. The health of our planet is often measured by how well the plants on it are doing. And this is a great image example also by Curtis Seaman of the northeastern United States in this kind of true color image. So this is what you would see in, say, late summer over New England. And those of you who live in New England or who are from New England or who have been to New England know that in the fall you get these beautiful changes of color. And so we can switch to a fall image, and you can actually see those red colors popping up all along the border of Maine and Canada through Vermont and New Hampshire and northern New York. You can go back and forth and see the effect of the season changing on the Earth. Now that's a beautiful thing to look at, and it's wonderful. It also tells us something about the climate. As the planet warms or cools, the dates of when those leaves changing also changes. So by using satellites to measure where this leaf change is happening, you can actually get some basic idea of the impact of any potential climate change on the Earth. And that's something that scientists are very interested in looking at as well. Moving along, fire, dust, and aerosol tracking. The ability to look at the Earth in true color is really important to be able to distinguish between smoke or dust or aerosols from clouds. And on the upper left is a picture of the High Park fire. It's a picture actually taken right out of my boss's window. There's a wildfire here in Colorado, for those of you that don't know, that happened starting the 8th of June in 2012. I remember that day very well because it was the day my second daughter was born, so we had to bring her home from the hospital in a huge cloud of smoke. And these smoke plumes are very, have a lot of impact on the country. They go way downstream, all the way through Nebraska into Iowa. They cause health issues, and being able to track that as opposed to clouds is very important. Also, dust. On the image down upper bottom left is a dust storm, I believe over China, that was seen by astronauts. And so they're the people that can really kind of see where these dust storms easily. The image here on the right is actually forest fires from that Himawari imager. This is that advanced baseline or advanced Himawari imager that is a twin sister to the ABI. So we'll be able to see images just like this from GOES 16, And you can see along the southern coast of Borneo here a series of fires, and it's very difficult for a satellite algorithm to detect these things, but for human eyes that are trained at seeing things, you and I can actually look at that and say, oh yeah, that looks different. That looks different than the clouds. It's obviously something else, smoke. And with the high resolution in time, we can go in and watch that fire burn. We can watch and see where that fire may be spreading and get better ideas of where that smoke, where that pollution is going, and have better air quality forecasts. So there's a lot of really good things that are going to come out of this satellite package. Tropical storms is a huge one for us here at CSU, and for everyone across the country. Those of you who live in Florida know the impact of tropical storms in your lives. And the image on the left is actually a true color image of Hurricane Matthew as it was transiting between Hispaniola and Cuba prior to coming up and giving us all a big scare as to whether or not it was going to wreck GO-16 on the launch pad. And finding ways to get high definition, high resolution, both in space and in time, pictures of these satellites is really critical to finding out where the center of these storms are, which leads to better forecasting of where these storms are going to go. And the images on the right are actually from, again, Himawari 8, which has the same instrument that GO-16 has on it. And these are two images of Typhoon, oh, I've already forgotten the name. I think it starts with an M. This is a super typhoon from October 19th of last year as it's coming in towards the Philippines. And the top image is actually one of those nighttime observations. So you can actually see these storms very well at night based on the several channels. It gives you so many more channels that you can see where these things are, and that helps you find out where they are. On the left of that, you can see a little bit of the city lights of the Philippines. That's actually a product that is added into. It's not something that the satellite saw directly, but it's something that we can map on to the satellite image to tell us when those satellites are moving over populated areas. And then the bottom image is actually one of these. It's black and white. It's that super high resolution red channel that lets you see a ton of structural detail of these storms. And that's something that's really, really important to note, that we're still trying to understand how these storms work. And so getting very high resolution of the cloud tops, seeing where the storms that make up these hurricanes are, come from, where those cells are, how fast they're moving around the eye, what happens to them as they move around the eye. These are all things that we're going to be able to do with much better ability because of these new satellites. We're not getting one picture at 1 kilometer every 15 minutes. We're going to be getting half a kilometer pictures every 30 seconds, and that's going to give us a bunch more information to tell us how these storms work and live. So to sum up a little bit about the benefits of GO-16, again, we're expecting way better hurricane track and intensity forecasts. We're going to know a lot more about thunderstorm severity. That's going to help us get better tornado lead times. Aviation flight routes, we're going to have a lot more information about where to best route aircraft to minimize flight delays and bumpiness, turbulence, icing. All of these things are going to be improved with our ability to see more colors of light in the sky. Higher resolution data for long-term climate studies. That's a really big thing. The better quality the data is, the better confidence we have in our ability to model the climate, and that's something that everyone's interested in, I think. And there's a lot of other features that we didn't cover in this talk. There's more instruments on GO-16 than just the few I talked about. They have space instruments that are designated to looking at space weather and the sun in particular, and solar flares, which have a big impact on radio communications and GPS communications, and just the EM health of the planet depends on monitoring solar flares. And so GO-16 has a high quality solar instrument that's designed to look at space weather and solar weather. My specialty is on Earth weather, so I didn't talk much about that, but there's plenty of information online, and I'll give you a link to that to see how that works just very shortly. And then improved search and rescue tracking. Because they sit up over the Earth looking at the same part of the Earth all the time, it turns out that geostationary satellites are very, very good at looking for SAR signals. So if you've ever gone out on a sailboat, for example, you may have a satellite warning system where if the ship's going down, you can push the uh-oh button, and that sends out a signal to these geosynchronous satellites. They can locate where that signal is coming from and then notify the Coast Guard to go out to that location and find where it is. And so that's another incredibly useful feature of these geostationary satellites. that I didn't really get into. So with that, I want to thank you for your time. I left a little bit of time for questions here, so hopefully we'll have some good ones. And in the meantime, I'll bring up this page of links. On the top is the GOES-R homepage. That's a really good place to go to learn about the GOES-R program and GOES-16, the satellite in particular. Certainly a good place to see when data starts coming out from the satellite, which again should be any time now. They have a great frequently asked question page, which you can follow by that link. Many of the products that we create here at CIRA, we have a proving ground page where we're testing out these things that we're going to be using on GOES-16 when the data is live, and that's a link there. NASA Space Place is something that I've been involved with and written several articles for based on GOES-16. And there's great projects there for school children and adults and people who are just interested in learning about how the science works. Certainly on social media, I would encourage you to follow the NOAA Satellite and Information Service on that Facebook link. And then, of course, CIRA is active on social media, and that's our Facebook link and our Twitter handle if you want to follow us to get updates. So with that, I guess I'll hand it over back to Henry, and we can field some questions.
Hey, thanks, Matt. Great presentation. Boy, we learned a lot, and it was good stuff. We're going to keep these links, or we will put these links on our web page. So if you go under CoCoRaHS WeatherTalk webinars, and then you click on Matt's webinar at the bottom, you'll see not only will you find this webinar archived on a YouTube channel, but we'll also have the slides that you can go back and look at, and then all of these links. So a lot of information. If you've missed anything or have any questions about, you can definitely take a look at that. Well, if it's time to type in your questions, and wow, the board is lighting up here with a lot of questions. Here's one coming from Randall. Wants to know, will GOES-16 cover Hawaii?
That is a great question, Randall. So right now, GOES-16 is set up over 89.5 degrees west latitude. The coffee is not kicked in. I apologize. So right now, I don't think they're trying to figure out where they're going to station GOES-16, and it'll either go to the west, in which case it will cover Hawaii, or it'll go to the east, in which case it won't. Right now, it does not cover Hawaii. They have not determined where it will go, and I'm not sure when they'll answer that. The good news is, if they move it to the east and it doesn't cover Hawaii, GOES-S, when it launches and becomes GOES-17, will be stationed, and you'll see Hawaii with it. So eventually there will be full coverage of both oceans using our satellites. So short answer is not sure yet. Stay tuned and we'll find out.
Matt, and I may have missed it. GOES-S, what is the time frame for that? Do we have anything yet?
You know, it's my understanding is it's undergoing instrument testing right now. When you build a spacecraft, there's a lot of things that have to be tested, especially when you're launching to geostationary orbit. When you go to 22,300 miles away, there is no chance ever to go up and fix it. It's not like the Hubble. You cannot go up there and fix it, so it has to work right out of the gate. So they do a lot of testing in vacuum. They test all the instruments very carefully, vibration testing, and so my understanding is that GOES-S is still undergoing a lot of those kinds of tests and will be ready you know, eventually in the future. And there's a lot of scheduling for when the launch pad's available, when launch vehicles are available. I don't have a time on that. Maybe some more knowledgeable NOAA people do, but I'm not aware of when that's going to go.
And how big a jump is the GOES-R from its previous satellite? I know we've had many GOES satellites go up over time. Kind of, if you could kind of look at it like the iPhone. You know, the iPhone 4 comes out, and 5's like, nah, not so much difference, and 6, and then all of a sudden a new one comes out. It's a big change. How would you rate this?
If we're using phones as a metaphor, we're going from flip phones to probably I would say the iPhone 7, or maybe even like a head-mounted VR camera. It really is revolutionary. When you look at what scientists want to know, the nitty-gritty of it is in the differences between the different kinds of light. Looking at the different channels, you have to have high enough resolution to see useful things. You know, a thunderstorm may not be bigger than 4 kilometers, so you can't really see it at night. But if you have more channels to look at that thunderstorm at higher resolution, there's a whole bunch of things that we just couldn't see before that we're going to have really good information about now. So it's a huge leap. You know, it's almost like going from a landline phone to an iPhone. the kinds of things we can do with it is really revolutionary.
Thanks. We've got a lot of questions. Let's get to those right now. Gail in Austin says that she's in love with this satellite, and will GOES 16 be able to see changes in CO2 in the atmosphere?
That's a great question. I don't think there's any plans to look at that right now. The kinds of light that CO2 emits are within some of the bands of GOES, but not at the sensitivity level needed to really say something good about CO2. There is a mission called OCO2, the Orbiting Carbon Observatory 2, and that one is designed, it's a polar orbiting satellite, and that is designed to look at the changes of CO2, and that's a NASA mission, and I would certainly encourage her to look up the OCO2 mission to see what they've put out. That's a mission that I got to work on very briefly before I came over to CIRA, and it's a fantastic mission.
Great. John's writing in from Utah, and he wants to know how long is the GOES 16 satellite expected to be functional? So I know some of these satellites have a date when they kind of go out of use. What's the plan here?
So I think ideally you're looking for many years out of these GOES series satellites. The plan was 30 years, so 15 years from launch. The first satellite going through 2036. You know, space is tough. You can launch a satellite, and sometimes they go bad after a couple of years, and sometimes they live for a decade or more. GOES-R is a new. These are new instruments. It's everything new. I think they'll last quite a while. I think you're looking to get at least 5 or 6 years out of each spacecraft. They do have, you know, GOES S, T, and U lined up. So there are plans to bring up replacements, and typically what you have with our current GOES series, we have GOES West and GOES East, and that's GOES 15 and 13 respectively, and there is a GOES 14, which is also sometimes known as GOES South, and it's sitting in kind of a backup role. So it's not so much how long you can get out of the satellite, because you can't really plan that based on the vagaries of space weather. But do you have enough satellite spacecraft up there to be a backup so you have constant coverage regardless? And that's really what the GOES-R program is designed to do, to have that constant coverage regardless of what happens to the spacecraft all the way through the end of the mission and probably beyond.
Okay, great. Here's one, Michael, and Michael, I'm thinking the same thing with this question. How will we access real-time imagery and data from GOES 16? So how can we get our hands on that once it's available?
So for the average user, I would say the best way to do it is to get it right from NOAA. There's going to be a lot of data sources that are available online, and of course when you look at your weather news, if you look at Good Morning America or whatever TV show you happen to watch, not that we're endorsing any of them, your favorite weather channel is showing images from satellites, and that's your GOES data right there. That's the data that goes in there. So certainly go online. You can go to our CIRA page as one source for great GOES observations. And then also the National Weather Service will have satellite imagery over your area, and that's going to come from GOES.
Okay. Gary writes, is wondering, you mentioned about like if your boat was lost at sea, can the satellite help find aircraft that crashed in the ocean like the Malaysia Airlines a few years back?
That's a good question. So a lot of aircraft do carry these search and rescue transceivers or transmitters. The problem is if the aircraft sinks, those transmitters usually can only go through a couple meters of water. So once it goes below that, they won't be able to send a strong enough signal to be detected by the satellite. But aircraft carry them. You can actually buy individual handheld radios, in fact, that will alert them. Some of these spot receivers work kind of the same way, that they send signals to these constellations of geostationary satellites and can pick that up. So it's not just boats, it's any instrument that carries one of these transponders.
Great, and here we go, make sure we're still on there. So John was asking about, and you mentioned this earlier, about lightning monitoring. Will that data also be available to the public? I know Lightning's a lot of proprietary stuff right now with that, and will that be a product we can see?
So everything that's coming from the GOES project is paid for by your tax dollars, and everything is available. So yes, all this data is going to be available for use. There may be a certain level of scientific background needed to really use it well, but I think there's going to be a lot of people interested in putting together products that the average person can use. Maps of where lightning strikes are happening are going to be things that we're going to see in the next coming years. So yeah, all of this is going to be available to use.
Okay, Dave writes in and he wants to know how many people are needed to operate and analyze this data that comes in.
Wow, that's a big question. So NOAA has obviously their own branch of people that are working with it. There are companies that help build the instrument. They're helping out with the initial data processing and are going to be involved with that. Here at the Cooperative Institute for Research in the Atmosphere, for example, there's probably 10 or 15 people that are looking at this at a reasonably full time. And the deal is there's so much data coming from these satellites. It's going to be something of like 22 terabytes a week of data from the satellites that you could never really have enough people. So whatever number you put to it, there's more, and that's kind of an exciting thing for us. Is there's a lot of things we can learn about the Earth from these satellites. So really, it can take as many as you want. For the operational stuff, probably the teams that NOAA already has is sufficient to cover it. But there's so much that can come out of it that really the sky's the limit as to who could find this useful.
Thanks. James writes in and he wants to know how big in size and mass is a satellite? Is it kind of like a school bus or a Volkswagen or my desk or what?
Okay.
What size?
I'll rewind a little bit on my presentation here and see if we can give you a sense of how big the spacecraft is. I don't have the number off the top of my head, but I would say it's probably the size of a large SUV, if I can scroll through my presentation to get a picture. So here's a picture of the rocket. The width of that fairing is 15 feet across or so, about 5 meters. So I would say it's probably maybe 25 feet long or so, so maybe more like an RV or so, RV sized. And I can get you the exact numbers on the dimensions of the spacecraft a little bit later. But it's a reasonably sized spacecraft. It's not the size of a school bus, I wouldn't say, but maybe close to a school bus. It's a good question.
Great. Yeah. Now here's the next one. William writes in and he wants to know does provide a channel between clouds and snow cover? Will you be able to tell the difference to delineate between the two?
I think absolutely. There's a lot of different channels that we can look at. If you look at the physics of how light works, light reflects off of clouds and reflects off of snow, and they look relatively the same. But if you look at different channels, when you start looking at the emission of light, snow will emit a little bit differently than the clouds will. And there's lots of different ways that we can use all these different colors of light to get some information about the difference between cloud and snow. And that's one of the things that the natural color product can look at and distinguish between snow cover and cloud cover.
Okay, great. Steve is wondering, and you went over this a little bit, the deployment timeline for public distribution of the imagery. And you mentioned to us yesterday as we were talking that as the satellite unfolds now and it just gets up there, it's got to kind of degas and the glue's drying on these parts. Can you talk a little bit about that?
Yeah. Hopefully it's not glue, but yeah. So when you
Elmer's glue, they use it.
Yeah, it's surprising what you build these things out of. But yeah, so you launch a spacecraft, especially when you're going as far out as geostationary orbit, and there's kind of a long setup. So we hit orbit kind of end of November really, and you're deploying satellites. You're trying out the computers. You're trying out the radios, the various antennas that all communicate with the Earth, making sure that they're sending good data. And in the meantime, all the things that make up the satellite. In the vacuum of space, there's a lot of byproducts and whatnot that will slowly kind of evaporate away and they boil off in the vacuum of space. And it's to be expected. There's no way to completely clean these satellites. And you have to wait for them, essentially, before you open up the optical tubes or the optical assemblies. You want to make sure that all of those things that have boiled off have drifted out of the satellite. You can't use fans in space, obviously. You're kind of waiting for these things to boil off and drift out of the spacecraft before you start opening things. You want to make sure that the temperatures are all stabilized and that everything is basically where it wants to be for years of good operation. And so you take a long time getting spacecraft set up before you really turn on all the cameras, turn on all the radios, fire everything up. You do it very slowly and you do it very carefully because, as I said, you can't fix it if it breaks. It's there forever. So I think they opened up the instruments sometime in the last couple of weeks. They have some preliminary data coming down. They're checking it out to make sure it's working. I don't know any specific details, but everything I've heard is that it looks great and everything's going to be fantastic. And when they're ready to get some new images, that's going to be made public, and I think we're all going to be wowed by it.
Okay, Ray writes in from Missouri and is wondering if there's a lot of redundant systems on board the actual spacecraft in case anything goes down. I mean, is there a second camera? Is there what?
That's a good question. And I think when we look at NASA, we look at spacecraft, we think a lot about redundant systems based on when humans are flying. You have 3 or 4 systems sometimes that make sure that human life is preserved. When you start talking about robotic spacecraft, you can do that, but there's a certain expense that goes. These ABI instruments, they're unique, they're really one of a kind, and they're fairly expensive. And so when you look at it from a cost perspective, it may be cheaper to get a couple years use out of it before it fails and then launch a second one as your backup, as opposed to putting 2 instruments on every satellite. So the program managers that engineer these things sit down and do a cost-benefit analysis and find out, is it really worth it to have backup systems on this system or on this system? And I think for a lot of the systems, the communication systems and probably the propulsion systems, there's some backup capability. For the large instruments themselves, they're pretty much their own thing. They're large enough and they're expensive enough that you really can't do that. Another thing to consider is that launching things to geostationary orbit is very expensive. So if you double the weight of the satellite by putting a second instrument on, that makes it that much more expensive to get to orbit. You have to have that much bigger of a rocket. Everything gets much more expensive when you start putting a lot of redundant systems on these spacecraft. So for anything where human life is involved, the cost is no consideration. You put lots and lots of backups on. For spacecraft like GO-16 and other satellites I've worked on, sometimes you don't have backups. And I worked on a satellite that launched, and they didn't have a backup system for the fairing to fall away. That fairing didn't fall away, and the spacecraft crashed into the ocean and never made orbit. And that's just one of those things where it would have been too expensive to put that backup system and too heavy to put that backup system on the launch vehicle, and that created the entire mission. And that's just kind of how it works. Space is hard, and what you have to do is do it right the first time.
Okay, William writes in. He's wants to know that again here, the resolution of the lightning mapper. How does it compare to the National Lightning Detection Network?
So that's a great question. The National Lightning Detection Network is a series of small networks kind of around the country. I think my understanding, and I'm not a GLM expert by any means, but my understanding is that the resolution is very comparable. I'm looking up some details on that right now. But the real benefit is that we're going to have half a global coverage. So places where there is no lightning detection network, okay, where they don't have towers that are looking at what the resolution is. Say, for example, over the tropical Atlantic Ocean, we're going to have detection capabilities there where before we had none. So it's not so much the resolution. I guess the spatial resolution is about 8 kilometers nadir, 14 kilometers at the edge of it. And I'm not sure exactly how that compares to the lightning network. I'm not a lightning person. But really the benefit there isn't so much the resolution as it is the global coverage and the ability to see lightning in places that we've never seen lightning before.
Lloyd writes in and he wants to know, will GO-16 have the ability to sense auroras? Will you be able to pick those up?
That's a good question. I don't know. I wouldn't expect it to, but you'll probably see something. When you launch these satellites, you're never sure what you're going to see until you turn it on. And that's the case with one of the satellites that we launched earlier, a polar orbiting satellite called SUMI NPP, or JPSS-1. And it launched with a low light sensor that we weren't expecting to see. We were expecting to see some nighttime cloud stuff, but we ended up seeing a whole lot more properties of the atmosphere than we thought. In terms of aurora, it's the emission spectrum for that is within almost one of the one of the visible bands on GOES 16. We'll see if the strength of the aurora is strong enough to be able to see it. I guess we'll just have to see. It's possible, but I don't think it was planned to.
Well, Matt, we're at the top of the hour. Can you hang in there a few more minutes? We've got some more questions. Does that
Sure.
work for you? Okay, great.
Yep.
Let's take a couple more of these that we've got out there. John has got two questions. He wanted to know, well, it's all combined here, talk more about measuring water content. So the water content in clouds and precipitation, that type of stuff, he wants to know, is that what you're talking about when you say water content?
Yeah, that's one of the things you can look at. Water vapor, which is of course the gaseous form of water, emits at a certain frequency, and then that relates certainly to when there's clouds and how much water is there. And they're looking at different techniques, again, using different colors of light and our knowledge of physics about how water and clouds interacts with that light gives us ideas a little bit about how much water is in the cloud. Another thing we can do is with that geostationary lightning mapper, we know that to make a bolt of lightning you have to have a certain amount of updraft in the cloud, and that updraft contains a certain amount of water, and that gives you a rough idea of how much water may be falling out of that cloud as precipitation as that lightning is forming. So there's lots of ways to measure, water content in clouds and vapor content over non-cloudy areas.
Okay, here's a real technical question, and we may not even understand this one, but this comes from Jim, and he wants to know, he understands that with between the Himawari 8, I'm going to read this to you, AHI, and the GOES 16 ABI, one of the differences is that GOES 16 will have a 1.378 micron channel for detecting very thin water clouds during the day. Was there a reason that that channel was decided when GOES 16 ABI was being designed or built? So why that channel?
That's a very good question. That's obviously from someone that's inside the business. And so that's he's talking about channel 4 on ABI, and if you want to go up and pull up a ABI channel band, it measures between 1.371 and 1.386 microns, and that's a daytime cirrus cloud band. And if you're looking at one of the things you can use for that, thin cirrus are actually fairly important for the Earth. Different kinds of clouds do different things within the atmosphere. It turns out that high clouds tend to help warm the planet a little bit. Low clouds, on the whole, tend to cool the planet, and that's a function of how well the clouds trap infrared radiation and warm the planet versus block sunlight, which cools the planet. So these high thin cirrus clouds are very good at trapping some of that infrared radiation, but they don't let very much light. They let a lot of light through. They don't block very much light. And the thing is, they're very hard to see. They're very thin cirrus. But we can see them at this one frequency of light that corresponds to the ice crystals that make these clouds up. And so understanding where where those clouds are is something that's very important, and having a satellite that can see that constantly is a big deal. And so that maybe kind of answers the question. You pick that channel that we have that the AHI, the Japanese instrument, does not have, because that's what we wanted to see here in the United States. And that's something that you're always kind of doing when you're designing these instruments. You have a certain amount of bandwidth, and you have all these channels. What do you want to see? What's the priority? And there's panels of scientists that kind of come up with, here's the important things that we want to see. Here's what we should have on the instrument, and then design it that way. And I think the importance of seeing these daytime thin cirrus clouds is probably worthwhile.
Okay, we've got a couple more here. So John is writing in, and he says, the new ground installation radars that are out there now provide enhanced level weather data, the cloud types, the lightning. Do you have any effort to integrate your data with these stations? So the combination of the dual pole and so forth with you guys.
Yeah, absolutely. Anytime you have multiple data sets, there are whole fields of science that are dedicated just to bringing them together. Radars give us incredible options to see the shape of hydrometeors. Certainly when you're looking at thunderstorms, what's that updraft actually doing? If you compare that to, say, the geostationary lightning mapper, that gives us a chance to really calibrate that instrument, because the benefit of a satellite is you have observations where you don't have radars. There's no radars at sea. There's not radars in large swaths of kind of the Great Plains, the upper Great Plains. So, calibrating the satellite based on what the radar is telling us gives us almost the value of the radar, but over the entire globe. And then the satellite can also provide some information to the radar scientists as well. So absolutely, there's going to be a lot of collaboration between those different stations, making both products better.
Okay, here's one from Christopher, and he leads, he's a leader for storm chasing teams, and he was wondering how the new satellite might benefit a storm chaser in the field during a tornado warning. If so, how will it predict the tornado movement more than we can see from on the ground?
So one of the things that GoCoRaHS is going to be able to do, and I would tell Christopher to hang on and wait till he sees one of these high-res super rapid scan images, you're going to be able to see overshooting tops with incredible clarity compared to what we're seeing right now. Plus you're going to have 5-minute resolution. That's at least as good, or 30-second resolution. So as a storm chaser, he's used to kind of 5-minute radar updates. He's going to be getting 30-second updates of what that overshooting top is doing. If there's any back building, if there's any change in the storm structure, you're going to see storm splits much easier. And then a lot of the research side of it is, what are the relationships between, motion in these cloud top, these overshooting cloud tops that we can see with GO16 that we can't see with other geostationary platforms. What are the relationships to updraft strength and rotation and the strength of the tornado? There's going to be a lot of studies in the next couple of years to kind of come up with, there's some hypotheses on relationships that may influence tornado development, and we're going to be testing those hypotheses using GO16 observations. So from a strictly, sitting in your car pulling down the data stage, you're going to see an incredible amount of high definition detail at just crazy resolution that's going to help you kind of see what the storm is doing. And then from a research side, 5 or 6 years down the road, we're going to have a lot better idea about the physics of what's going on inside these storms that will make better forecasts and then get more information out to the community.
Okay, Bob's been waiting a while for his question here. He wants to know, I know you mentioned about picking up tree images and so forth, the vegetation in the Northeast. Are there images of all the dead trees caused by the drought in the Sierra Nevada and California? Are you able to pick that kind of stuff up with this?
I think so. That's one of the things that biologists are going to be looking at forest health. Of course, right now you can't really see anything because they're all buried under 15 feet of snow. But looking at beetle invasions, I work with a scientist at the National Forest Service who's really interested. National Park Service rather. No, sorry, he's the National Forest Service, who's really interested in looking at what GO16 is going to be able to do with certain colors of light to see if he can actually look at beetle stress in some of the larger national forests. So it's certainly possible. I think there's going to be a lot of research going into that. We're going to be able to see things just with our eyes using true color imagery and using human intuition as opposed to relying on a computer's interpretation of a black and white image. There's things that our brains see that just can't be matched by algorithms yet, and that's going to be useful.
Okay, we've got 4 more questions out there. We're going to ask you guys to hold off on questions now as we're starting to run out of time, but a lot of great questions, and thank you for asking them, everyone. Dave in Arizona wants to know, will GoCoRaHS cover New Zealand? Will you guys get in the southern hemisphere with this?
That's unfortunately, we're not going to be able to see New Zealand. This is a project paid for by U.S. taxpayers, and so they're going to put it over areas that are directly looking at the United States. But I would certainly encourage any Kiwis out there to check out Himawari 8, which does see New Zealand quite well. And I'll scroll back here and can show you a picture of what we can see with New Zealand. So here you can actually see, we'll pop forward here. So New Zealand's, of course, down here in the bottom right, so you can actually see Himawari 8 has a pretty good view of New Zealand, and any interesting weather events over there will show up on that satellite. So you get the quality of ABI and GO16, but from the Japanese agency.
Great. Michael wants to know, being a CoCoRaHS observer, how might CoCoRaHS play a role? So might CoCoRaHS significant weather reports and other citizen science observations, would they develop focus for things you guys might want to look at and so forth?
What I'll tell you is that when I talk to National Weather Service forecasters, CoCoRaHS is incredibly valuable data. I myself am a CoCoRaHS observer. I absolutely believe in the power of that system. And anything where we're developing new algorithms that are related to precipitation, using GOES-16 data, or co-locating that with GLM data perhaps, looking at rainfall. If there's anything that comes out of that that can be ground truth by dedicated observers making regular observations, they're absolutely going to use that data. CoCoRaHS is probably one of the greatest citizen science projects I've ever been happy to work with. And the data is really high quality, and certainly if you're taking those observations, you're part of the mission and you're helping with that.
That's great to know. I'm sure that's very encouraging to all of us out there that take our daily observations, that you don't really realize what are observing, where they're used, and they're used all over the place. That's neat.
Absolutely.
Well, Sud here has got two questions. I'm going to combine these quickly. He wanted to know about improving wildfire forecasting in real time, fusing with the MODIS. And then he's got a little more of a technical question here about what standards and formats the data will be provided in. NET CDF, CF convention, or HDF 4/5, if that makes any sense to you.
Yes, it does. So to the first question, fire weather forecasting, when you look at wildfires in areas, the High Park fire that I referenced from 2012 is a fire that started from a lightning strike that smoldered for several days before finally breaking into an area of extreme beetle kill, very dry tinder, and then spread very, very quickly into a very, very large fire that impacted hundreds of people and caused a couple of fatalities, sadly. So having the ability to see where lightning strikes are over areas of concern, where there's drought, where there's a lot of dead trees, where the humidity is very low, all of things which GOES-16 is going to help see, gives the opportunity to see where you might have a nascent fire, a small smoldering fire like what the High Park fire started out as. And if you have the ability to see these small fires before they get big, it's a heck of a lot easier to send in a helicopter and dump a bucket on it when it's a small fire, rather than finding out when it explodes into a much bigger fire and having to deal with the millions of dollars of firefighting and evacuation efforts. So just the ability to see these things before they really get big is going to make a big impact on our firefighting capabilities. As far as the data format, I'm assuming they're going to come down to HDF. I have to look that up, actually. That's a good question. I haven't seen any data from GoSAR yet. It's going to be coming through, right now it's coming through the Harris Corporation, which helped build the instrument. They have their own file system, I understand. I'm not working with the data, but I can certainly put you in contact with the people that are working with that data if it's something that you're interested in working with the raw data. My understanding is that each channel, each of the 16 channels, has their own file, which I believe are HDF, but I have to double check on that. But yeah, so each channel is going to have its own file and be processed that way.
Okay, last question of the day. John wants to know, would it be possible to combine GOES satellite imagery from stereo imagery?
Oh, so in terms of using, so if we had two, so when GOES-16 and GOES-17 perhaps are in orbit on different latitudes, looking at the continental United States and then combining them. And that's a great question, and that's something that we actually already do with our current GOES series. If you're sitting at GOES East, which is out at 75 degrees west, if you look at California, you're looking at California at a very sharp angle, and when you see the clouds, you're seeing the sides of the clouds, and that gives you some information about the vertical structure of those clouds. GOES West over at 135 west is looking at those clouds a little bit more top down. And so there already are ways to look at the 3D structure of the atmosphere, combining stereo image from both satellites. And with GOES-16 and then with GOES-S, once it launches and hopefully becomes GOES-17, we'll be able to do the same thing.
Okay, I've got one last question for you. Several folks may be going to the American Meteorological Society conference in Seattle next week. I know a lot of times they have things on display there. Do you know if they'll have the satellite on display or a replica? Any information on it?
Unfortunately, I'm not going to AMS, but if I were a betting man, I bet there'd be a lot of good information about GOES-16 at the AMS conference in Seattle. So certainly swing by the NOAA desk and the NASA desk if you're there, and you'll get a lot of information about GO16 from there. And just to go back to the question, it looks like right now the data is available, sample data is available in netcdf format if you want to get your own GOES-R data, so that's netcdf.hdf.
Well, Matt, it has been a pleasure to spend this hour and 15 minutes with you. Wow, a lot of stuff we've learned, and we really thank you for taking time out of your busy day. I know you're a busy man to do a CoCoRaHS webinar with us, so thank you so much.
You're certainly welcome. I hope you had a great time, and feel free to ask any questions, and I will try and answer them as best I can.
Well, folks, we're going to wrap it up here for today, but I want you to mark your calendars. Now, we're going to a bi-monthly, so that means every other month webinar for webinars for 2017. And so join us for our next webinar, and that'll be on a Monday, so a little different than what you're used to, but Monday, March 20th. And I think that's the first day of spring. I'm not sure. Noah, if you can look that up maybe for me and as I'm talking here. To let us know that. But Scott Denning here at Colorado State University will talk about carbon in the atmosphere, and that's a very interesting subject. We hope you'll go online. We'll have the registration up for that next week, and so please join us for that. And finally, when signing off today, please, again, take that survey that'll pop up on your screen. That'll let Matt know how he did and us as far as with these webinars. So, folks, until the 20th of March, which could be the first day of spring, this is Henry Regis for the rest of the CoCoRaHS headquarters team saying so long for now, and we wish you all a great weekend ahead. Thanks. We'll see you later.